According to Einstein's theory, radiation conveys inertia between the emitting and the absorbing bodies. That means when I shine this light directly onto this apple, the flashlight will lose a small amount of mass because it's radiating energy. The apple's mass should actually increase by the same amount because its inertia increases as it absorbs the radiation from the light bulb. Let's get specific about this and crunch some numbers. If my flashlight emits a constant 10 joules of energy per second forever without failing or shutting down, how long would it take before its mass would be diminished by 1 gram? How long before my digital kitchen scale could tell me that it's gone from 50 grams to 49 grams? Take a wild guess or do the calculation yourself. You have all the clues you need to do the calculation. You could even pause the video if you'd like. I'll tell you the answer is that it will take a really long time. It will take almost 300,000 years for my flashlight to diminish by a gram. I don't know about you, but I don't have that long to wait around and see if this theory is true with an experiment. I can't put it to test in some underground laboratory that I have with a secret tool set that's a lot better than what I have. So we'll just have to rely upon math. Good thing it's trustworthy. Now remember that the primary purpose of equations is to describe relationships between quantities such as mass and energy. We can create equations with one or more variables and use them to solve interesting problems where we don't know the value of one of those variables. For example, we don't know how long it will take for my flashlight's mass to go down by 1 gram. We know how much energy is required, but we don't know how much time that will take. So we need to do the math step by step. Let's start with the original equation that was in Einstein's paper, m equals L over c squared. We should actually replace c squared with a number that's appropriate to convert between grams and joules. So I will say that m is equal to L over c squared, which is equal to L over 9 times 10 to the 13. Now, if we substitute 1 gram in for the mass, then we get 1 gram equals energy over 9 times 10 to the power of 13. If you want to solve for the energy, L, you can simply multiply both sides of this equation by 9 times 10 to the power of 13, and you get that L equals 9 times 10 to the power of 13. In an earlier video, we said that my flashlight will emit a constant energy at a rate of 10 joules per second. We're going to represent that here by saying that the energy produced per second is 10. And in a similar way that we did up here, we're going to isolate L and put it in terms of the other quantities. So we'll multiply both sides of this equation by S, and we get that L equals 10S. Now what we have here is two equations with two variables. We have a variable S for time, the amount of time it will take, and L for energy. What we want to do is get rid of energy because we're trying to solve for time. So we're ultimately going for S equals some number. We want to know how many seconds will this take. And all you have to do is use this equation and substitute it into this equation. What I mean is that these two expressions both express L in a different way. But these are equivalent expressions. So instead of L up here, we can have 10s. And now that we've done that substitution, we have an equation that has only one variable, s, and it's the variable we want. That's great. So we're almost done. We need to solve for s, and the way to do that is to divide both sides of this equation by 10. And you get that s equals 9 times 10 to the power of 12. That's how many seconds it'll take. Then it's just a matter of figuring out how many months, days, years that will convert into. So you just need to divide the seconds by 60 to get the number of minutes, divide that by 60 minutes in an hour, divide that by 24 hours in a day, and divide that by 365 and a quarter days in a year, and you get that my flashlight will diminish by 1 gram after 285,193 years. Boom. That is our answer. Nice job crunching those numbers. High five. So let's go back to the graph and see how this relates to the equation.